In this video, we're going to continue our discussion of Markov decision processes. So, as a brief review, in last class, I talked about probability notation just to make sure everyone's on the same page about what we mean when we write probability quantities out. Then we also talked about from the previous video Markov decision processes, which are ways of representing state spaces or environments where our actions lead to a probability of moving from state to state. Right? So we write down a transition probability given an action and given a current state where we end up. Then we talked about value iteration, which is an algorithm for computing the optimal policy to take in these Markov decision processes. So the algorithm basically works by computing the utility values of every single state, where the utility values are the expected future rewards, assuming you continue to play optimally from that point on. Okay, so in this video, we're going to talk about an alternate algorithm for finding the optimal policy, so something different than value iteration. And then we'll talk about how we can extend the concept of a Markov decision process to a situation where the agent doesn't have full observability of the environment, meaning it can only get partial observations, and it can't tell exactly what state it's in, and so on. So the alternate algorithm we're going to talk about to compute the best policy given an MDP is called policy iteration. And it basically takes the idea of value iteration and wraps it up in a different view. So remember that in both these algorithms, the main goal is going to be to compute the solution to the Bellman equation, which is on the screen right now. So this is the Bellman equation, and you'll recall that basically what it means is that the utility value is the reward you get right away plus the expected future utility if you continue to play with the optimal policy, which is very recursive. It's a recursive concept, which is why U appears on both the left-hand side and the right-hand side of the equation. So another way you can think about this is that the policy is going to be computed as the argmax, as the maximum scoring action, given the transition probabilities and the current utilities. So that means that we can then write the Bellman equation in a different way using this definition, using the definition of pi, the policy. We can say that the Bellman equation is basically this, right? It's that the utility is equal to the reward plus the expected utility, assuming that you're going to play the expected future utility, assuming you're going to play according to the policy. And now these are exactly the same thing. We haven't really done anything. We haven't really done anything other than reorganize, where that max occurs. Right? Originally, the max was in the Bellman equation, but now the max is kind of hidden away in the definition of the policy. But what is interesting about this is that assuming that the policy is fixed, assuming that pi is just something we can look up, then there's no more max in this modified Bellman equation on the bottom. All there is a bunch of numbers, which are the probabilities, being multiplied by the utilities, and what that means is this is a linear equation. And in fact, if you think about how many states we have to consider, we have to compute the utilities for. We have to compute one utility value for every single state, and we also have one version of this equation for every single state, right? Because this function takes in s as a parameter, so it takes in all the different states and outputs some value. So there are number of states total equations and number of states total unknowns. So if you remember linear algebra, this set of linear equations is solvable. So we can plug it into our favorite linear algebra toolbox, or do it by hand, or whatever we want. And we can solve this equation and get the exact values that make equality for a fixed policy pi. So what that means is that we basically have just it's closed form, meaning we can just solve for the exact solution It turns out in practice we will use, approximation algorithms or iterative algorithms. But the point is we basically have a function, right, that says, give me a policy and I will tell you the exact utilities assuming that policy is correct. Or we'll solve this bottom equation exactly, assuming the policy. So then the task for us as the Intel AI algorithm is to try to find the right policy, because whatever policy we pass for this function, it's going to tell you the exact utilities according to that function. And so then it turns out that the iterative algorithm is exactly as you would expect. Is that you start with some random policy, you pass it into this function, you get back the exact solution to this set of linear equations, and then you update the policy according to assuming that those utilities are correct, right? So you just sort of take these two equations and iterate them back and forth, where the bottom equation is actually a system of linear equations that we have to solve. So that's expensive, but it actually can converge faster in some cases, depending on maybe the complexities of the state space, or various other things. But the other thing to keep in mind is that we can actually do something kind of in between both models. So we can do, instead of updating the utilities by solving the equations, which is a cubic time operation in the worst case, we could actually just iteratively try to solve them with a essentially a value iteration algorithm where we don't do the argmax, we just assume the policy is fixed. So we can run this iterative algorithm until the u's converge, and then update pi. Or we could run this algorithm like a few times, whatever our time budget allows us. We run it for as much time as we have available, then we update pi. Or we can run it just once and update pi. But if we run it just once and update pi, then all we're doing is exactly value iteration. So it sort of shows that value iteration is like one extreme version of policy iteration, and then policy iteration allows us to get a more precise estimate of the utility u before we update the policy pi. So that's good news, but there's some bad news. And the bad news is if we just pop up a level and think about, what have we done so far? We've looked at methods that essentially compute this utility value, which is a function that takes in a state and it has to have an answer for every single possible state. So, right, it computes a utility for every state. So that's expensive. Right? We've never, up until now, up until we got into the MDP framework, we haven't really ever considered, an algorithm that would have to have an answer, a value for every single possible state. Right? That's just too big. If you think about realistic settings, the possible states in your environment is just humongous. So that's not great. Another thing that's not great about what we've done so far is that we also need to know the exact transition model. We kind of need to know exactly how the universe is going to work that we're going to be operating in. Right? This whole environment, we have to know exactly what happens. If we choose this action, if we choose to move our wheels to the right, or use our wheels to move to the right, we have to know exactly what the probability is we're going to move to the right, and exactly what the probability is our wheels will slip and we might stay in the same place or we might slide off to the side. Okay, that's unrealistic. And we also need to fully observe what state we're in. Right? We have to have sensors that tell us exactly the state of the entire environment. And so that's a little bit unrealistic too. And finally, we need to know the exact reward for every single state. So we have to have an actual R of S value for any state that we can consider, any state that is in our state space that we want to be able to reason about. So these are all not great things. But first, in this video, we're just going to talk about how to correct one of them. So we'll talk about how to correct the problem that we need to fully observe the state. And let's talk about why this is an unrealistic assumption. So when we think about Pac-Man, it's kind of an unrealistic situation because, well, we are this sort of omniscient, controlling being. We have the controller for Pac-Man, and we can see the entire screen. We can see the entire board. and we, based on where everything is on the entire screen, we decide whether to move left, up, down, left, or right. Um, that's the video game view of things. But in reality, or rather, if Pac-Man were a real thing, I guess if we can call it that, then it would really be like a robot that can sense just the things around it. Maybe it can see a little bit further in front of it, but and maybe it has some rear view something, I don't know, it's a radar or something behind it. Um, and what's tricky about this, right? Obviously, is that it doesn't know anything about everything outside of the square. It doesn't know anything about what's beyond the walls that it can't see past. And the other thing that's weird is that this state that is being observed by Pac-Man right here is exactly identical to this state up top, right? So it's the kind of thing where given what Pac-Man is able to observe, given the percepts available to Pac-Man in this view, it doesn't know. There's no way for the agent to know whether it's currently at the bottom of the board or the top of the board, even if it has the map, even if it happens to have the map available. So if it knows that the map is of this structure and there's two straight walls on the left and on the right, it doesn't know if it's on the top or the bottom of the board, and it doesn't know if there's a ghost in front of it, and it doesn't know if it's already cleared a bunch of pellets in the front or if it still has a bunch, a bunch in front of it to capture still. So we'll talk about how to extend the Markov decision process view of the environment to a situation where we have partial observations. So here's how it's going to work, and we're not going to get too detailed into this. I'll show you the basic principle behind it and how we can work with partial observations. But there's a kind of when we get to the end, you'll see why it gets a little bit algorithmically tricky, and pretty much this is active research of how to efficiently handle this situation. But I'll show you the basic principle behind it. So it's going to be something called partially observed Markov decision processes, or POMDPs is what they're affectionately called, I suppose. So the idea is that we're going to say we're going to have an observation model. So the observation model is going to be the probability that we observe some evidence E given that we're in state S. And what this captures is the idea that sometimes we're going to have some noisy observations. So not only will we have partial observations, but we also allow for noisy observations in the sense that we might have a radar that will malfunction every now and then. So we'll get a blip on our radar. I don't know if those of you who drive have some of these newer cars that have like the backing up radar, the radar behind the car. For me, a lot of times it beeps when there's actually nothing behind me. Maybe there's a speck of dust or something that passes by, and it beeps and it thinks that there's something behind me. Now, that to me means that I'm not necessarily. I might be about to back up and hit a pedestrian, but I might also not be. And so there's a certain noise model that I have in my head, and that we're going to also try to model mathematically with these things. In addition to this, we're going to try to handle the fact that we don't know what state we're actually in by exactly representing that. We're going to have something called a belief state, which is going to be a probability distribution over, what state do we think we're in given what we know. And that's a little bit vague right now, but just the basic idea is just we want to represent a probability distribution over the possible states we could be in at the current time. Okay, and we're just going to write that with a shorthand of just B of S. So B is this belief function, and S is the state, and it just returns the probability that we're in that state. Okay, and then what's that going to translate to? Well, so let's think about what do we know so far. We know the evidence that we see every turn that we've taken so far. Okay, we know the evidence. Whatever we're allowed to observe, we can theoretically we could remember all of that, but it turns out we don't have to remember it all. But the idea is that's what we know so far. And the other thing we know is which actions we've taken. Okay, so we know which actions we've taken, but we don't actually know what the result of those actions are. Remember, right? This is a Markov decision process, so there's noise in what happens when you choose an action. You might not succeed in that action. You might not succeed in the original intent of that action. Instead, you could end up in some other state. And so we have to keep track of all that stuff at some point. But but just to list the things that we know so far. We know the evidence that we've seen throughout the life of the game or the life of the agent, and the actions that the agent has taken. So this is how you would write down how to compute the uh, belief state given that information that I just described to you, right? So all we need to know here is the evidence that we've seen so far, which is what recursively is used to compute B of S, and then B prime of S is this updated version that takes into account the current evidence. So see, you see the first term has the P of E given S prime, and the second term, or the summation, sums over all the possible states we could have previously been in, based on the previous beliefs, of what probabilities we have for each state. Okay, and just as a refresher, this symbol here is the proportional to symbol, and so all it means is that if we wanted to treat this as a probability distribution, we'd have to normalize over all of these values to get it to be to get the sum to 1, so it's a valid probability distribution. But that's normally some people could write that with just a constant that you multiply everything by, but sometimes it's easier just to write proportional to so that you don't have to write out those constants. Um, and let's just look at each piece of this equation just to break it down. So the right side thing, all the way on the right, is the previous belief state, or current belief state, depending on how you look at it. But it's the old belief state. Okay, it says what is the probability that we're in state S given everything we've seen previously. Okay, and then this is the transition probability. This is something we've seen. We should be comfortable with traditional MDPs that from the last video and from the last class. Right, this is just the probability that we're in state S prime, given that we used to be in state S and that we took action A from state S. So when you put these two things together, you actually get that this basically represents the probability of a new state given the previous belief. And then we also combine that with the first term, this P of E given S prime, the observation model from the very the second line of this slide. Right, that's something that we're given, that we assume we know, and so it's something we can compute. We can just look it up, and what that buys us is that explains why this is how we should update the beliefs, the probability distribution over what states we think we're in, according to the previous probability distribution and the new evidence that we get. Okay, so let's put that expression aside for a second and think about, what we're going to try to do is we're going to try to write a POMDP as an MDP. And there's going to be some caveats, which is why I put sorta in the title. But the idea is, what we want to do is we want to write a POMDP, or rather, we want to write an MDP, a fully observed MDP, over the belief states, over the state space of the beliefs. So that means that our state space that we're going to search over is the state of all possible beliefs. So that strictly generalizes the original formulation, right? The original formulation was the state spaces of the states. Now we're going to talk about the state spaces of the beliefs, which are probability distributions over the states. Okay, and so the two things we need to make this work are, we need a reward function for belief states, okay, and a transition model. Right? If we have those two, then we just have an MDP, and maybe we can just run our traditional MDP algorithms that we've already studied, like value iteration or policy iteration. Okay, so let's try to do those two things. So the first thing is the reward function. So the reward function, originally we had a reward function that takes a state as input and outputs a score, outputs some reward value. Now we don't have just a single state. We have we have a probability distribution over states. That's our belief. So it's pretty simple. The reward function on the top left it just sums over the beliefs of all the states and their respective rewards. Meaning this is actually the expected reward, right? If B is actually a probability distribution, which we've designed it to be, then this is the standard expression for the expectation of R, given that we're going to randomly sample what state we're in from B. Okay, so it's pretty straightforward, right? That makes a lot of sense. So okay, we're on the right track. We've got a reward function for B. All right, so now we also need a transition model. So the transition model, again, think about it this way: if we have a current set of beliefs, um, B, we call them B, um, and we take action A, what will our new beliefs be? What will B prime be? That's the transition model. And what we're going to do is I'm going to show you how to derive these equations. And the bottom line that I'm going to spoil ahead of time is that you can write this down in a way that we can compute it from the things that we already know, the things that we've already discussed. The first thing to note is that this expression, the probability of B prime given B and A, it doesn't say anything about the state or the evidence. And everything we've written down so far, everything we've described so far has pretty much reasoned about the state and the evidence. Um, Sometimes the state is reasoned via the probability distribution over states, our B's, but there's always some notion of state. So let's try to write this expression in a way that includes both the state and the evidence. And so this new equation, this new form, is exactly equivalent to the expression above. I just switched the order of A and B, and then what I've done is I've summed over the probabilities of the B prime and E and S, and the evidence and the state, or the new state rather. And it's not really this doesn't change the number. That doesn't change the value because previously we were just considering the probability of B prime given B and A, and now we're considering these other variables, right? These E and S variables, but we're summing over all the possible values of those variables. So it's essentially like those variables become background once we finish summing them all up. But writing it this way is going to help us write out expressions that we already know how to think about. So breaking this up further, we can do something called the probability chain rule, which allows us to break up some of these variables into conditional probabilities. I wouldn't worry too much about this at this point, but the idea is that everything upstairs is still down in this equation, this new equation in the middle, and one thing to note is that we at least have identified one thing that we know, right? So that P of E, the thing in the middle, P of E given S prime, that's our observation model, right? And that's, again, as part of the POMDP framework, that's given to us, okay? And then this expression on the right is something that, okay, let's think about what this means. This says what's the probability that we end up in state S prime given our previous beliefs B and an action A? And so we can do this again. We've done something like this already, and we can write an expression that sums over all of the previous states. So this sums over all the previous states, but then considers the probability that we're in that state from our beliefs. Okay, and then what we have is a bunch of expressions that we now know how to think about. So this is our observation model, like I said, and this is a traditional MDP. Or rather, it's the same transition model from our traditional MDP. So we also have access to that. And then finally, we have a belief. So that's just our beliefs. So for sure, everything all the way on the right is something that we can compute. Everything I've drawn arrows to. So now what about this weird P of B prime given EAB expression? So this one's a little bit weird, but it turns out that this is actually just a deterministic function. It's not really a probability distribution. It's just an indicator function that checks whether B prime is equal to the update equation that I hid in the corner, right? That we talked about in the previous slide. And this is just, when we update B prime to that value, we're going to have to multiply it by the rest of the equation. And that seems a little bit weird, but it's important to think about, where's the randomness coming from in all these probability distributions. So moving all the way from the right to the left, the belief state is the randomness is in, what state are we in? And the MDP transition probability, that comes from the noise that's innate in the environment. And then the observation model also comes from noise innate in the environment, but with respect to our sensors, not with respect to how we transition between states, but how we are able to sense evidence given what state we're in. And then the P of B prime given EAB, that was just, it's basically just an algebraic trick where we isolated the actual randomness is on the right, and then on the left is just a deterministic function of how we decided to update B prime, right? And we decided based on the update equation on the bottom. Okay, so don't worry about this too much. The idea is that this is now an MDP over continuous belief state space, right? We now have a reward value for any belief state you pass into the reward function. You get a reward value out that you can compute using the previous rewards that were with respect to the actual states in the state space. And then we have a transition model that says that if we're in belief state B and we take action A, we have a probability distribution over belief states B prime. Okay, and that's great news, right? It seems like we're done. We could just run value iteration or policy iteration and we'd be done. Okay, the problem is that the state space of all beliefs is, I already told you it's a generalization of the original state space, but it's an infinite state space because it's a continuous state space over all probability distributions, and as long as you have more than two underlying states, it becomes there's infinite ways you can write down probability distributions. So it doesn't work as great as with a traditional MDP. But what we can do is something that we won't do in too much detail. But the idea is that we can write down a few things, and it will sort of hint at how POMDP methods work. So we can write down this expression. It's called alpha P of S, and what it means is it's the utility of a plan P from the state S. Right, so a plan is a sequence of actions. So it's like, I think last video I showed you a sequence of actions that didn't work so great in a Markov decision process. But given that we have a fixed sequence of actions, we could write down, we could try to compute this. We could compute the utility of the plan, given that you start from state S and you take the sequence of actions. It's the same kind of computation we've been doing previously. You sum over all the possible states you could end up in after you take these actions, and you sum up the rewards. It's not too important. So now, what can we do with this? Well, we can actually now say, remember in a belief state, we have a probability distribution over what state we're currently in. Well, so that's great because now we can say, here's the expected alpha for some plan P and the current belief state. Right, so this is now, the expectation over what state we're currently in of alpha, which is the utility of what happens if you make some plan P starting from the current state. Okay, and that's good, but now we can go even further because we can say, if you think about what the utility values are in MDPs, or rather in the value iteration algorithm or policy iteration. Right. The idea is that it's the score you're going to get if you play the optimal policy moving forward. So we can write that down in this form as well. We can write down that the utility for being when you're in state B is the maximum over all possible plans you could make. All possible plans, which essentially means the maximum over all possible plans is going to give you the optimal policy of this expected utility. Okay, so using this form, the book gives an algorithm for computing these alphas, but it's pretty slow because if you think about it, we need a different alpha for every single possible plan, from here now until infinity. So that's infinitely huge, but it does have some structure that you can take advantage of, and so the book has some algorithms for doing it, but it's still not ideal, and so it's still an area of ongoing research how to efficiently represent these things. And you can imagine taking this and coming up with approximations, looking at this form, right? It's a nice linear form. You can come up with approximations, and we'll kind of get to that sort of approximate utility function later on. So this video covered policy iteration, which is just more or less just a variant of value iteration, where you can update the policy iteratively, but then update the utilities by solving for the utilities. And then we talked about partially observable MDPs, where basically the general strategy is to reduce the problem to a fully observable MDP in a continuous search space or state space. And things get tricky from there, but there do exist algorithms to handle that. And you can read about these in chapter 17.4. And even though I sort of mentioned last video that you can skim the rest of the chapter if you want, really the important stuff for the narrative of this course really ends around the end of 17.4. The rest is more about game theory and things that are a bit outside the scope of what we're going to look for. So have a look at chapter 17.4, and then next class we're going to get to some really cool stuff. So this is that list of complaints I had about what we've done so far in MDPs, right? You had to compute a utility value for every single state, and this was even further compounded when we went to continuous state space with the beliefs. We also required that the algorithm, the AI agent, also needs to know the exact transition model, and that's just totally unreasonable because in the real world, if we knew the exact transition model, then we could just run everything basically in a search framework. The whole point is that this noise is difficult to understand, and then we also required that you need to fully observe the state, which the POMDPs somewhat attempt to address, but still introduce some new problems that we have to handle later. And then lastly, we need to know the exact reward for every state, and that's a little bit weird too, because what you would imagine a situation that would allow that would look like is that there's a robot that's in some start state, maybe it's at the beginning of some maze, and somehow it just sits there and thinks really hard about what reward it's going to get as it reaches different states in the maze. And the idea is that we're going to look at these two complaints, and what's going to happen is that the most natural way to make these more realistic is to consider learning agents. So this is going to be an agent that's going to exist in the environment and perform some actions and get some feedback. And its feedback is going to be based on the actions it performed. And then based on that, it will update some representation of the utility or something. We'll get to exactly how it's done. But the idea is that we don't have just some agent that can just sit there and think about the world and then come up with a plan of action or policy. Instead, it's going to explore the world, get some feedback, and try to learn from its experiences. So I'll introduce all these ideas next class, and but if you want to read ahead, you can have a look at chapter 21. That's where all this is on. This is about reinforcement learning, and I'll talk to you in class.